So this is the first lecture in a series of lectures for Melius Mentorship, and we're going to be looking at Chemistry 12. And we're going to start with the first unit on reaction rates. So reaction rates are the measurement of a change in the amount of something with respect to time. Now, how we write that typically in the correct way is with this symbol here, delta. Delta means change in. So if we have a change in the amount of a particular reactant or a particular product, then we put delta to show that. And this is all with respect to time. So reaction rates always have a time component. So let's look at some ways in which we can measure reaction rates. And the simplest way is to measure the change in concentration. So in this reaction, A plus B goes to C. Now, in what we can do to measure the reaction rate is we can be like, okay, let's measure the change in concentration of C with respect to time, because the concentration of C will increase as the reaction progresses. If C is a gas, then we can also measure the change in the pressure with respect to time. Pressure is also a concentration, something sometimes people forget that. The other ways which we can measure reaction rates is through mass changes. Now, just to clarify, a change in mass is usually going to be something we have to do with reactions where there is a gas involved. So gases, they escape open systems. So if we had a reaction here and it was giving off a gas, then the gas will escape and the mass of the container in which the reaction is taking place will decrease. And we can measure that change in mass with respect to time. The next one is color changes. Now, these are typically done through specialized equipment called spectrophotometers. Now, what they do is that they measure the change in absorbance of a sample. So if we have blue food dye and bleach, for example, so we have food dye and bleach, if the food dye absorbs 420 nanometers, and in this reaction, the food dye goes from blue to colorless. So it absorbs in the blue region. That doesn't mean it emits in blue, but it absorbs in the blue region and it becomes colorless. So what we can do is we can plot what we call an absorbance time graph. So we have absorbance, and then we have time. And as the reaction progresses, if the color is changing and becoming colorless, let's say we add the bleach here, we can measure the change in absorbance with respect to time. So color changes can also be used. So let's have a look at an example of how we would calculate a reaction rate. So what is the rate of reaction when, for example, 23.5 grams of magnesium is used up in 6 minutes? So let's say we have this reaction, Mg plus O2 goes to MgO. So let's do that. Let's have a look at this reaction. So what's going to be happening is we have 23.5 grams of magnesium and we have an excess of oxygen, and we're saying that 23.5 grams is used up in 6 minutes. Well, 23.5 grams, then we have 6 minutes. And so the rate of reaction is 3.9 grams per minute is being used up. So this is a fairly simple example. What about this one? Let's say we have an aluminum solid and we add HCl and we get this reaction here. So the production of hydrogen gas is 0.06 grams per second. Sorry, just to clarify that I am obtaining these questions from a source or an online source. So I will link that source, and I want to credit the individual who has kindly put out this great resource. And that is this website. It's Marie Eve Owen for the BC Chemistry 12. So I believe that I will link this website for people to have a look and attempt some of the problems. So thank you very much, Marie Eve Owen, for providing this. Okay, so we have this following reaction: 0.06 grams per second. So that is the rate of production of this gas. Now, one question we need to ask is, well, okay, so if that's the rate of production of this, how do we find the rate of production of this? And how do we find the mass that has been reacted of aluminum? So let's start with that first. How much aluminum reacted in 3 minutes? Pause the video and have a go at the question. So we have 0.06 grams of a hydrogen per second. Now, hydrogen weighs 2 grams, and that is for 1 mole of hydrogen. So we can now convert to moles per second. We know that 3 moles of hydrogen reacts with 2 moles of aluminum. So now we are in moles of aluminum per second. We also know that the molar mass of aluminum is 27 grams. Then if we multiply that by the time, because we are in seconds right now, and we have 3 minutes, well, that will be 180 seconds. So what we have here is that, exactly. We have figured out the amount of aluminum that reacts in 3 minutes, and we can check our units here. So as you can see, at this point we're in grams per second, and we've multiplied by seconds to find the amount that is reacted in those 3 minutes. So the other thing to consider is, what happens to the reaction rate during the course of a reaction? Does it go up or does it go down? Pause the video and see if you can answer the question. As the reaction proceeds, the rate of reaction decreases. Why? Well, reaction rates are contingent on concentration. So let's say we take this at time t equals 0, and we have 6 moles of reactant. So A, and then B, B. So A plus B makes C. So this is at time t equals 0. Let's say at time t equals 2, some of the A and B have been converted into C. So if A plus B goes to C, then what we will have is the following. So AB, this is C, and A and a B joined together. So as you can see, we've actually used up 2 A's and 2 B's, and we started with 3 A's and 3 B's. So right now all we have left is this. So these are the only things left to react. So the concentration of the reactants has decreased And when the concentration of reactants decreases, the rate decreases. So, that is the basic introduction to reaction rates. Let's have another look at some more important notes, and especially on how are reaction rates affected. Okay. Factors affecting reaction rates. Okay. So, let's start off with the most basic factor that affects reaction rate. Temperature. Why does temperature affect reaction rate? So reactions are collisions between molecules. Now, when we have a reaction that contains, molecules A and B, these molecules have some repulsion between them. And this repulsion is more importantly classified as activation energy. Now let's explain what that is. When we look at these two, they don't just necessarily come and collide with each other to make AB. They need energy to do that. This will not happen without enough energy. So let's see what happens when you increase the temperature. When you increase the temperature, you increase what we call kinetic energy. And what this means is that when the temperature has increased, the kinetic energy of reactants A and reactants B has increased enough so that they can collide with each other. And this is important because the more kinetic energy there is, the more often they will collide. And the more often they will collide with enough energy. Because if you think about it, if you put 5 people in a room and you tell them to walk around, they won't really bump into each other. But if you put 5 people in a room and you tell them to run around, it's more likely that they'll bump into each other because they're moving faster. They'll see each other more often. In addition to that, they'll collide with more force. If they walk into each other, it's not going to hurt. But if they run at each other, it is going to hurt. So that means that the collision is of more energy. That's why temperature increases reaction rate. Another thing that increases reaction rate is concentration. The reason concentration increases reaction rate is because there are more molecules of the reactants. And when there's more molecules of reactants, they will come into contact with each other more. So, as we increase the concentration, the rate of reaction goes up. Pressure, as I mentioned before, also actually increases reaction rate. That is because pressure is analogous to concentration. Now, there is the nature of reactants. So, certain reactants will react faster simply because they are more reactive. For example, sodium will react faster than lithium when you put them in water. The reason is because sodium is more reactive. That is because sodium can lose an electron more easily than lithium. We don't have control over this aspect. So, let's have a look at another factor, which is surface area. The greater the surface area, the larger the reaction rate, because when there is more surface area, there is a bigger area for successful collisions to happen. Let's take something like a piece of metal. Now this is just a rectangular piece of metal, but let's say we ground up the metal into a powder. When the metal is in a powder, it has more surface area, which means that reactant molecules, so the second reactant, let's just say A reacts with this metal. Now, when A reacts with the powder instead of the sheet of metal, there is more area for A to collide with, which means that the rate of reaction is higher. The last, or second to last rather, I'm going to talk about is catalysts. Now, what is a catalyst? A catalyst is something in a reaction which increases the reaction rate but is not changed at the end of the reaction. So, I'm going to show an example. A plus B plus C, where C is the catalyst, makes AB. Now, this is a bit weird because, well, how is C the catalyst? So, in these reactions, what we have is the catalyst will first do something like this. A plus C goes to AC. Then AC plus B goes to AB plus C. Now this is a bit confusing, so I'm going to explain exactly what's going on. So, catalysts are regenerated in reactions. So what do we mean by regenerated? See, the catalyst originally reacts with A to make AC. Then, when AC reacts with B, it displaces the catalyst to regenerate it. So as you can see, something is a catalyst in a reaction if it is consumed and then it is produced. And why do we use catalysts? Well, catalysts, they act in ways to lower what we call the activation energy of the reaction. The activation energy is the amount of energy required for a successful collision. And a successful collision is a reaction. So, because the catalyst lowers the amount of energy, more reactants, A and B, have enough energy to make AB. Now, the catalyst is always going to be regenerated. If something is not regenerated in a reaction, it is not a catalyst. AC is what we call an intermediate. Now, an intermediate is a molecule in a reaction, or a complex, that is produced and then it is consumed. So it's produced here, and then it is consumed here. And so a catalyst, strictly speaking, it offers an alternative path for the reaction. So, these are broadly the main things affecting rates of reaction. So, one thing that we should talk about is which reactions would be the fastest and which ones would be the slowest when we have the following. So we have calcium oxide reacts with carbon, goes to calcium carbide plus carbon dioxide. Then we have another reaction So, which one is fastest, reaction 1 or reaction 2? Well, the answer to this question is the following. Reaction 2 is faster, but why? Aqueous ions react faster than solids. Why is that? Aqueous ions can move around quite easily. And that is because they're dissolved and they have a lot of free motion. So what that means is that they will come into contact with each other more, and so they react faster. Solids, because of their restricted motion, will come into contact less frequently, and the rate of reaction will be lower. Typically, when we react solids, we have to heat them quite a lot in order for them to react. Broadly speaking, ions, oppositely charged ions, react faster than gases and liquids, which react faster than solids. Solids usually react the slowest. So, this is the first section of this series of lectures. We've discussed what affects rate of reactions and how we measure it, and this is hopefully useful for your studying. Thank you and bye.